In this video, we'll be going over the big ideas of chapter 6 and 7. So the first thing we talked about is the inverse of an exponential function. So there are two reasons why we started talking about the exponential function. The first one being you should be really good at it. You should know the graph of an exponential function. You should know the properties of an exponential function because that was what you studied in grade 11. And the second reason is because we're going to talk about the inverse of an exponential function, which is actually a logarithmic function. So by using your understanding of an exponential function, your ability to learn about the logarithmic function is greatly enhanced. So don't think of the logarithmic function as something entirely new. Just use what you know about exponential functions to help you with your understanding of logarithmic functions. So the first thing you should do is graph a logarithmic function, or just any logarithmic function, let's say a base of 2 or base of half, and then establish the properties. So for example, what is the vertical asymptote, x-intercept, y-intercept, domain, range, increasing, decreasing, and where it's positive, where it's negative, all that stuff. And hopefully you'll see the relationship between the properties of a logarithmic function with the properties of an exponential function. So after you're comfortable with that, then we talked about going from logarithmic form to exponential form. This is very helpful because it helps us evaluate logarithms, because your understanding of what a logarithm is depends on your understanding what a power is. So let's say 2 cubed is equal to 8. Because you know 2 cubed is equal to 8, then it makes sense that when you evaluate this logarithm, log base 2 of 8, it makes sense to write 3. Okay, so your understanding of going from one form to another really helps you evaluate logarithms. Okay, because really I think of a power when I'm trying to evaluate this logarithm. And secondly, you want to be able to go from logarithmic form to exponential form because there's nothing wrong with x equals 2 to the power of y, but because we want to express y explicitly, so y in terms of x, you want to use logarithmic form. Okay, so logarithmic form was very powerful. It allows us to express y in terms of x and help us evaluate logarithms. So of course, after you learn about logarithmic functions and how they look, you transform them. I'm not going to spend too much time on that, but I will say one thing about the vertical asymptote. You really want to graph the vertical asymptote to help increase the accuracy of your sketch. And the location of the vertical asymptote is dictated by the horizontal translation. Okay, so after transformations, we talked about these tools that we're going to use for the rest of the unit. We talked about the power law of logarithms, the change of base formula, the product law of logarithms, and quotient law of logarithms. So I really want you to relate. So when we did the lessons, we proved the power law, change of base, we proved all of them. But in addition to being able to prove these laws or the change of base formula, you really want to relate the power law of logarithms with the power law of exponents because they're pretty much the same thing. They just look different. It's expressing the exact same idea as you did in grade 9. You want to relate the product law of logarithms with the product law of exponents. And lastly, you want to relate the quotient law of exponents with the quotient law of logarithms. So why do we learn these tools? Because they help us simplify logarithmic expressions. They can help us solve logarithmic equations. In fact, they can also help us solve exponential equations as well. And they help us evaluate logarithms. So it's really important you know these tools because you'll use them. These are the algebraic tools you'll be using for the rest of the unit. Okay, so after you learn those algebraic tools, we talked about logarithmic scales. So we did 3 scales in particular, but really you can talk about any logarithmic scale. And the idea is the same. You have values that vary over many orders of magnitude, and you want to be able to interpret them. So that's why you introduce a logarithmic scale. So some examples that we did were the pH scale, a decibel scale, and the Richter scale. After that, we did some more algebra. So we talked about solving exponential equations, and we talked about solving logarithmic equations. And related to this, you can also do the word problems. Like for example, for the exponential equations, you can do the half-life problems, or finding the time it takes for the car to depreciate to a quarter of its original value. So if you can solve exponential equations, you can do those word problems. One thing I want to add is when you solve logarithmic equations, you should check for extraneous roots. It's very plausible that you have extraneous roots. And to determine whether a root is extraneous, it would really help if you stated the restrictions to the equation. And that way you'll know for sure whether your root is extraneous or not. Anyways, those are the big ideas of this, of chapter 6 and chapter 7.